see here or no?
Oh, yeah, you can. Yeah, we can adjust it over your head if you're too tall too. So.
You see what he did on this one? Can you take over for a little bit?
Yeah, it's easier.
All right, so let's get started. So first of all, I'm gonna quickly go over the solution for homework 1, which I have released in Canvas already. I have also released the project description. So let's go over the solution really quick. So homework 1 solution. Let me open this using another icon. Okay. Problem 1. So there are really two things to note for the solution of problem 1. One is you need to use a hierarchical structure to represent males and female and animals. You know? That's kind of, I think most of you should be able to get that right. That's a hierarchical construct for that. What's tricky about this problem is how you represent the father and mother relationship, which I actually gave you a hint last lecture. What I said is, as long as it is an entity set, even though there are entity sets organized in a hierarchical structure, you may still have relationships that connecting those entity sets. Right? In other words, you can connect a parent entity set with a children entity set using just a normal relationship set. That's exactly what we do here, making the observation with the observation that only a male can be a biological father of another animal, and only a female can be the biological mother of another animal. Okay? Using those two observations, you will have to introduce these two relationship set called father of and mother of. And there are one to many between male and the animal entity set, and female to the animal entity set respectively. Why it is one to many? Because a male may be father of many animals, and a female may be mother of many animals. But for a given animal, you should have only one biological father, and you can have only one biological mother. So it's a one to many mapping. Let me finish and I'll take the question. Note that finally, so that's how this is set up. And furthermore, note that I didn't enforce total participation on either side. The reason is as follows. Yes, an animal must have a biological father and mother for the animal to exist in the first place. However, from the point of our database point of view, we may not care about his or her father or mother if that mother or father, which are animals themselves, are not part of my lab. If you do enforce total participation, then you end up with an infinite loop. Every animal needs to have their father and mother stored, which is animals themselves. Goes back and back and forth, go up all the way. You end up with an infinite size database if you do enforce total participation constraint in that way. Does it make sense? You follow the rationale? With that being said, I'll take your question.
So I was wondering why you would want to do have relations rather than just making them attributes. You could just have one father and one mother.
The attribute setup, what you are suggesting is the following. So what you suggested essentially is trying to confuse what relationship is trying to model with what entity set is trying to model. What you propose is, okay, what about just use animal? Right? Then I have animal ID. Then I have some other attributes. Then here I introduce the mother ID and father ID. That what you have just suggested? Okay. This particular design, if you think about it, what you're really doing is trying to model interaction between entities using attributes. We said multiple times in ER, interaction between entities is to be modeled by relationship. Right? So if you think about further, right, what you're really doing is jumping ahead. So in other words, how do we convert this to relational tables, by the way? For one to many, right, how do we convert this to the tables? We take the key from one side and play that into the many side. That's what we said, right? There are no separate table for that one to many relation set. What you have proposed is exactly that, which is you are taking the key, the mother ID and the father ID, which, by the way, these are just animal ID themselves. I just call them mother ID, father ID to distinguish them from AID. What you are doing is, suppose I were to convert those to tables, I will have an animal table, I will have a female table, I will have a male table. For the animal table, I will have these two attributes because I'm taking the key from the one set and place that into the many set. So what you have proposed is actually what the table looks like when you try to convert this to the corresponding table. But if you were to model this in ER, you lose the important information of the interaction between male and animal and female and animal. You lose that relationship for that reason. So that's over there. Now, another subtle point is concerning the test. Actually, one of you asked this question on Canvas. I actually kind of hinted, right? You need to make a distinction between the type of test and the instance of the test. These two are two separate objects for the following reason, because the spec clearly stated that an animal may take the same test multiple times. What that means is the same type of test. If you were to model this like, okay, I have an animal like this, entity set, then I have a test entity set. Then I just say, okay, you take this test, let's say many to many, right? An animal may take multiple tests, a test is given to multiple animal. If you were to model like this, what's the functional constraint? It's similar to the example we went over in our lecture, which is employee works for a department for the same duration. Do you remember this case I discussed? Employee, department, works in, from, and to. What's the limitation of this particular design? Well, the same employee may work for the same department only once. Right? Because fundamentally, for the same type of relationship set, and for the same two entities, you can only connect them once using that using an instance of that relationship. You cannot connect them more than once. In other words, you can only have one from two values, pair of from two values connecting these two entities. You cannot connect them more than once. Similarly, if you were to use a design like this, what you're saying is each animal may take the same type of test only once. Okay? Do you remember that discussion? And how we fix this here is, okay, in order to model the fact that an employee may work for the same department over different periods of time, multiple times, so what you do is you introduce another entity set called duration or period. And you introduce a ternary relationship between the three, so that the employee may work for the same department over different durations. And using this instance diagram, the picture looks like this. Okay. Now I have multiple different durations. I can connect them like that. Each of these three-line connections form a ternary relationship instance. Okay. Question over there.
So with that, is that you just said we can't, an animal can't take the same test twice, right?
With this design, no.
Yeah,
No, it cannot.
So, but if you have unique test IDs, wouldn't it be possible for the animal to take the same test multiple times?
Still not. Doesn't matter. I mean, even if you introduce the ID here, it still just identify this entity. You still have this barrier of the same entities can only be connected once using the same type of relationship. Okay? So that doesn't solve the problem. Of course, you may argue, I say what your argument is, my ID now is to identify an instance of test, not a type of test. But then the problem is, with that design, note that, that's why I made a clarification, I want to document the name of the test and the cost of the test. If you do that, result, date, name, and cost, this becomes a really bad design in the sense that for each instance of that type of test, you are duplicating the values of name of the test and cost of the test. You are duplicating these two values over and over and over and over and over again, which is a bad design for that reason. You follow my argument? But I see your point. Okay? That's why we want to model them as two separate entity sets. You can either use this two-binary relationship set. It is also possible to model the relationship among the three of them using a single ternary relationship set. That's fine as long as you model those participation constraint properly, meaning one-to-many. Why there's a one-to-many between animal and test event? For example, an animal may take multiple different test instances, but each test instance is given on a single animal. And there must be a total participation constraint on the test event because a test instance only exists when it is given on an animal. Otherwise, I don't really care about that. But an animal may or may not go through any test at all. So there's no total participation constraint on the animal set, but there is a total participation constraint on the test event set. Question over there?
Yeah, so with your male and female having their attributes, team level,
Body fat, yeah.
fine.
I think it was mentioned in the spec.
Blood cells.
Blood cells.
Okay, so change to whatever it was mentioned in the spec.
Either way, like, it's kind of not.
Can you speak a little bit louder?
Yeah, you can't really get to those values unless you take a test. So isn't that kind of like duplicating information?
Ah, I see what you're saying. No, you are over-interpreting what the spec says. I mean, the spec says T level and body fat are to be stored. It never asks you to store the information when these values were obtained. Does that make sense? The spec never mentioned that. So these are considered as a natural attribute of female and male, not associated with the test. Okay. All right. So that's so much I want to say about part one. The conversion of this to the relational models, I think is very simple, right? You just look at ER to relational model slides. It's very mechanical, right? You follow the step, and the rules we talk about. There's no way you can get it wrong. Okay? But the key point is when you are in the ER stage, do not think about tables. Do not think about tables. Do not think about tables. There are no tables at this stage. Okay? And then you convert this to tables, and you can check the solution yourself. I give you both the schema as well as the query table statement, SQL statement. Okay? So that's problem one. Problem two. First of all, there is a hierarchical structure for technician and traffic controller. They are both employees. And there is a plane entity set, obviously, representing each specific plane. And then the model, right? Boeing 737, Airbus 330, those are models, but I may have multiple planes of a particular model, so there is a one-to-many mapping of the two. And note that there is a total participation constraint on the plane side, but not on the model side. I may have a model that in my fleet, I don't have any plane belonging to that model. But every plane in my fleet must be of a particular model. So there's a total participation constraint on the plane side, but not on the model side. Do all of you follow me? Yes? Okay. The technician is an expert of certain model. He or she is not an expert of a particular plane. That's why there's a many-to-many mapping between model and technician, because a technician may be an expert of multiple models, and a model may have multiple technicians who are experts of that model. Do you follow the argument so far? And there is a task performed on a given plane, and each task has an FAA number, name and score, and I document the hours and dates of that task, and the score of that task. Okay? So that's kind of just like a ternary. You can actually do this using two binary relation set as well. Here I choose to model this using a ternary relation set.
Does this way mean that you can only have one for the same test?
But note that it's a ternary. By the same technician, yes.
Yeah.
By the same technician on the same plane, on the same task, yes. On the same type of task. But the technician, different technician can perform the task on that plane. Did you follow what I'm saying? Right?
Yeah. Well, which is more correct?
Well, the spec isn't really clear about that, right? If you want to make a differentiation over there, either way is fine. That's what I'm saying. Because the spec was really not clear about whether the same technician can perform the same task on the same plane multiple times or not. The spec didn't really clearly indicate which is the case, so either design is fine. Right over there?
So on that test info,
on that test info, yes.
So even though date's like an attribute of like the relationship set, like if you made that like a key, part of the primary key as well, I mean it wouldn't follow that, but that would make it.
So this was asked in Canvas as well. Relationship has no keys. Relationship has no keys. How do we identify a relationship? Relationship is identified by the two participating entities. That's why for a many-to-many, when we convert this to a table, when we convert the relationship to a table, the key for that relation to that table is the combination of the key of the two participating entities. Relationship has no keys, meaning that with this design, employee work for a department over different durations, you cannot simply say, oh, to fix that, I'm going to introduce a duration ID and here, and suddenly I can introduce multiple lines connecting the two. No, it doesn't work like that. Relationship has no keys. Relations have no keys. Okay. All right, so that's that. Now, question over there?
Is your line bolded from technician to expertise?
Say again?
Is the line from expertise to technician bolded?
Oh, that, in my design, I choose to bold it, but I think the spec didn't really say that, so either you bold it or not, it doesn't really matter. The spec didn't really clearly say every technician, does it say every technician must be an expert of some?
Yeah.
Okay, then it must be both, meaning that every technician must be expert of at least one model. That's why there's a total participation constraint on that. But the spec says nothing about each model must have at least one expert. That's why there's no total participation constraint on the other side. Question over there?
Yeah. Can you actually have with the relationship with test information and test both have scores? Or do they have to be different names to make them?
Oh, I see. I made a mistake because I shouldn't have the score attribute here. There's a max score, so this probably means max score.
Okay. So they have to be different.
Yeah. So the name has to be different. Sorry, I can do that. I will pick this. This would be max score, maximum possible score. Excellent. Okay. All right, cool. So that's problem 2. And of course, you take this design, you convert this to relational model using the conversion rules we talk about. The conversion itself is pretty do what I did.
Like I printed out a picture of what the table should look like.
Did you include create table statement? Because homework 1 asked, yeah, and you do exactly what I did. That's fine, of course.
I noticed. Okay, so for the employees, for the is it relationships.
You mean you want me to go back to the ER?
If you want.
Okay, sure.
So I'm wondering about the is it relationships. There's two options. One where you can have the 3 entity tables, and then one where you just have the 2. And what is the case where we can't have the 2?
Yeah. Okay. Very good question, by the way. So his question, let me repeat so you guys can follow. His question was, when you have a hierarchical structure, there are 2 options. One is to convert them into 3 tables. One is to convert them to 2 tables. Using this particular example, the 3 table setup will be employee table, technician table, traffic controller table. The 2 table setup will be to get rid of employee table altogether and only have technician and traffic controller table, right? In most cases, both options are fine. In some cases, you want to go with the second option, which is having only 2 tables, so you have 1 less table to deal with. If, and only if, the covering constraint is true, meaning that the union of technician and traffic controller is all your employees. In this particular case, the spec isn't really clear about that. So either way is fine. I don't really care which way you go. But if the spec clearly mentions that among my employees, some are technicians, some are traffic controllers, or some other type of employee, but didn't mention what additional information I care about those additional employees, but there is an indication that there are some other type of employees, then you will have to go with a 3 table setup.
Between your employees and your technicians, how did you determine how to split those attributes?
Well, those common attributes goes to the parent entity set. Those children entity set specific attribute goes to the children entity set.
Wouldn't salary be common across every employee?
Well, the spec, what's interesting about this is the spec didn't mention that I need to store the salary information for traffic controller. So you may, of course, I don't want to make a really big argument against that. In this case, whether you put salary as an attribute of technician or employee, I think either way is fine. But if you read the spec, according to this particular spec, it only mentions salary for technician, but not for traffic controller. So it indicates that maybe the owner only care about salary for technician, but not so much on traffic controller. That's why we choose to go with this. But either way is fine.
So with the covering constraint, like in the overlap, so like if you wanted to disallow overlap, would you have to do the 2-table approach versus the 3-table?
Well, 3 table will be okay for disallowing overlap constraint. Well, disallowing that in ER is easy. You add an annotation. Disallowing that in your relational model is much more trickier. You need to write a customized integrity constraint, which we haven't talked about yet. How to do that? Okay, we will talk about that later on. All right, so problem 3 is fairly, I'm not going to go over problem 3 here. You can read the solution itself. It asks you to have a design where it results in primary key, foreign key. I actually show you all possible different designs that will lead to a primary key, foreign key setup. Then it asks about this employee department duration setup, which is the one I just went over one more time. Right? We talked about that during lecture. I just went over it one more time. So you can look at the solution yourself. Okay? So that's so much about homework 1. Now let's talk about project. Okay? So your project is assigned today and due on, let me see. I think I make it due on the Valentine's Day. You have to have something to celebrate, right? And just submitting your project. That's a good reason to celebrate. So in fact, I'm doing you guys a favor if you think about it. And homework 2 will be released later today and due next Monday. Homework 2 is on relational algebra. Okay? So basically, what I thought about this, what I want you to do this year is Uber. Okay? You guys will build a Uber-like database. Of course, without building the front end app. That's the only thing missing, but other than that, you are building a Uber. We call this view Uber because we're at the view. But essentially, it's the same as Uber. You have Uber customers, Uber cars, which I call UCs. You have Uber drivers, UDs, and you have Uber users, UUs. Okay? So Uber driver and Uber user are different, right? As you can tell. Each Uber driver may have multiple Uber cars. Meaning when I register as a Uber driver, I may register no cars, or one car, or multiple cars under me. And each Uber car, you store some basic information about the car, right? The model of the car, the year of the car, the category of the car, whether it's an economy car, luxury car, comfort car, then you charge different price for whatever category you're in, right? For Uber driver, you document the name, SSN, and the availability, right? The time she or he willing to drive during the day. I don't care about the date, but I care about the hours during a day, any day, that driver is available. Okay? Then I have Uber users. Okay? So those are some basic data. Right? Any question on this part? So those are the three basic entities in our entity sets in our design. Then it asks you to have a bunch of functionality, such as, of course, you have to allow users to register either a Uber driver or Uber user may register him or herself to your system. And a Uber user may make a reservation ahead of time, meaning that I know tomorrow this time I'm going to use the car, so I want to make a reservation. Okay? The reservation is made with respect to a particular Uber car, rather with respect to a particular Uber driver. Okay? But of course, you have to check the reservation is made during the time for that car that associated driver is available to drive. Right? There is some simple constraint checking you need to do in your logic. Does that make sense? Also good? Then, of course, there's the rights, meaning that, by the way, a Uber driver may enter a new Uber car at any time. Any Uber driver may decide to register a new Uber car. And then, after a ride, a Uber user will document this ride into your system with his or her experience. Give a rating for this ride and a comment for this ride. Pretty much like you watch a YouTube video, you write a comment down below. Do you follow this? And what's interesting is other users may comment on your rating and comments for a Uber driver. Imagine I just take a ride, I comment on this driver. Some other user may say, and I said this is a fantastic driver. Another user may say, yes, I agree with Feifei. Another user may say, Feifei, you got paid by this driver. Do you follow me? So other users may comment on your comment to another Uber driver. And they may also rate your rating as useful or not useful in different categories. Okay? Like pretty much like in Facebook, you like or dislike a comment. Right? And then there are favorite cars, meaning that a Uber user after one or multiple rides of a car may decide to claim that car as his or her favorite cars. That's a simple functionality. Feedback recording, I'll talk about this. Usefulness reading, I'll talk about this. And users may form a correlation among that, meaning a user may trust another user. Okay? I trust this user. I declare this user to be my trusted friend. You may wonder why you need this. Well, later on when you do recommendation, those recommended cars from your trusted user will bear more weight than those you haven't trusted yet, for example. That's one possible application of this. Then there's a Uber car browsing. You may browse different cars by a combination of current conditions, like the model of the car, the rating of the car. Each car receives multiple comments and rating by other users, right? You want to browse those cars, for example, rating above certain threshold, or find all the cars in the luxury category sort by their average rating from high to low. Okay, so that's what Uber car browsing is about. Then there is useful feedback. You know, given a Uber driver ID, I want to find the top X number of useful feedbacks for the Uber driver, and which is calculated by looking at all feedbacks given to all the cars owned by that Uber driver. Each Uber driver may have multiple cars, and I aggregate the values of all the feedback to all the cars this driver owns and sort based on the average score of that, so that I find the most useful driver, second most useful driver, and so on and so forth. Okay? Uber car suggestion. When I was trying to make a reservation, if I'm interested in Uber car A, you should recommend another Uber car B if there is another user X who have hired both car A and car B in the past. In that case, you should recommend car B. And the recommendation should be sorted in the order of number of users who have hired both A and B, from high to low. You follow this? The intuition is very simple. If somebody has hired car A and hired car B a lot of time, then that's a good candidate for recommending to you when you are interested in hiring car A. That's kind of intuition candidate. Of course, in real life, the recommendation is done using much sophisticated algorithm, machine learning algorithm, looking at user backgrounds and what kind of ride you have taken. But here we're using a very simplified strategy for making a recommendation. Okay? 2 degrees of separation. Remember, user may trust another user, right? That's what I call 1 degree separation. If I trust user A, and another user trusts user A, but I don't trust that user, then this is called 1 degree separation. It's kind of like on Facebook, I'm friend with A, you are friend with A, but we are not friends together, then this is called 1 degree separation. Why this is useful? Because Facebook are interested in okay? Speaking of degree separation, there's a famous theorem which is called small degree, right? Which is to say any 2 people on Earth know each other without more than 6 hops, without more than 6 degrees of separation. Example, I know Donald Trump in 2 hops. You probably do as well. You trust me? Let me give you the example now. I know the president of the U. He must know the senator of Utah to know Donald Trump 2 degrees. No. And you are at most 3 degrees because you know me from Donald Trump. So don't think Donald Trump is some guy who is far away in DC. He is just 3 degrees away from you. Maybe less. I don't know. To give you an idea of what it is. And by that argument, I know the president of Syria in 3 degrees. I know Donald Trump, he must know this guy. Right? Like random person on Earth. Okay? So there's some other stuff you can go over yourself. Those are the basic functionality. Yes, I made it due on the Valentine's Day. So phase 1 is pretty much like your homework 1. The design phase. You have to come up with the ER diagram, the schema, the create table statement. That's it. Phase 2, I talk about phase 2 later on. Phase 2 is to implement all the functionalities in a standalone environment. Phase 3 is to move everything to the web environment. That's it. Okay? We will release the team assignment by hopefully before Wednesday. Everybody has signed up by now. I've made it clear that you need to sign up by Friday. For those of you who know your teammate is, you should start working with him or her. For those of you who decide to do solo, you should proceed. For those of you waiting for assignment of your teammate, we will do that by hopefully by tomorrow. I do want to mention one thing. This is a team project, right? I used to do this by without forming a team because I think there are many issues when we do this as a team. Meaning that when you have a teammate who is not very responsible, okay? Who says, I'm going to do this and that, but end up not doing anything, or end up doing a fraction of what he or she is supposed to do. Okay, things like that do happen. Okay, even if that person is your good friend, this may happen. Okay, trust us, believe it or not, this may happen, even if you're a good friend. So here's what I will do. If you notice any issue like that, you should let me know as soon as possible. If you're worried about the relationship with your teammate is not working out, don't worry about upsetting him or her. You can contact me in private first so that I can talk to the other person to figure out what's going on. And to a point, if the relationship deteriorates so much that you can no longer work together, we will break up the team and find out whose fault it is. The one at no fault will get a reduced workload for the remaining part of the project and do the project by him or herself with a reduced workload. The one at fault will do the project by him or herself without any reduction in the load. But you need to let me know ahead of time. You cannot let me know a day before the deadline, say, Feifei, my teammate is not doing anything. That's too late. Does it make sense? Okay? Any question on project? Are there?
One small clarification. So this project is going to get completed over the course of many weeks, and for now we just have to complete phase 1.
Yes, right now you only need to worry about phase 1 due in about 2 weeks.
Okay. So I thought phase 1 was just like individual, but we are supposed to.
No, phase 1 is project, the team setup.
Oh, right. Yes.
Yeah. Okay. Any question on this? No. So let's continue with the discussion on this. So last year we did Airbnb essentially. So this year we do Uber. So maybe next year you can tell me how I build something. Okay, let me show you. I will be excited about that. But the point is, for all these companies like Airbnb, Uber, all this, right? They are successful not because of the technology they use, really because of the business idea they have. Which is kind of cool, but at the same time kind of sad. I mean, I want to see more companies like Google, which is successful because of the technology of it, not simply because of the business model of it. Because if it is only because of the business idea, business model of it, anyone who has taken a database class with some idea can go out and build it. Seriously. There is no barrier. But if I ask you to build Google, even if I tell you all the business idea, business model they have, you won't be able to build it. Take time and take training. For Uber and Airbnb, anyone has some database training will be able to do it. All right. Of course, that's not to say they're not great companies. By the time they grow to the size they are today, they face a lot of scalability challenges as well. But at the beginning stage, really, there is no technology barrier from preventing anyone with some strong CS background to go about building that. But Google, even from the very start, the search algorithm they have, the PageRank, is not trivial. You need to have significant training in computer science, like a PhD degree, in order to do that. Okay, so now we talk about these examples. I'm going to continue from here. Find the name of sailor who reserved a red color boat. So how do we do this? Using relational algebra. Let me refresh your mind with the instance of the running example. We have reserved sailor and boat, showing who reserved what on what date. Okay, that's kind of the setup. And the query asks you to find out who reserved a red color boat. Who reserved a red color boat? How do we do this? So obviously, the information about the color of the boat is only available in the both table. So obviously, you need to do a join because the color of the boat is not available in the reserve table. In the reserve table, you can only find out which sailor ID reserve which boat ID. But you don't know which boat ID is associated with a red color boat. So you have to do a natural join between reserve and boat ID in order to find out those boat IDs that are from a red color boat. All of you follow this discussion? Then you will have to do another natural join with the sailors in order to find the name of the sailors who made those reservations. So that's kind of the idea behind the construction of this query. So option number one is you select those red color boats from the both table. Then you naturally join those with reserve. The natural join happens on the boat ID column. Remember, natural join says, I take two instances and enforce equality condition on common attribute. The common attribute between boats and reserve is BID. So I enforce equality condition on BID. That's essentially what happens over there. Then I take the resulting schema of the natural join between boat and reserve. I take the result of that and naturally join that with sailors. But now, if you think about it, the schema of that natural join is what? It's boat ID, color, name of the boat. You get rid of that second boat ID from reserve. You have SID and date. So the resulting table of that natural join has 5 attributes like that. And the common attribute of that with respect to sailor is simply sailor ID. So the second natural join happens on the sailor ID column with, again, equality condition on sailor ID, which is to find what sailor have reserved those red color boats. Then you put out the name, which will get rid of duplicates, meaning that if the same sailor has reserved the same red color boats on different dates multiple times, his or her name will show up only once in the end. Of course, this is not the only way to do it. Another way to, even more efficient way of doing this query is to say, okay, after I get the red color boat, I really only care about the boat ID. I don't care about, at this point, once I make sure I have only red color boats after that selection, I no longer care about the color, the name, and all other whatever information associated with the boat. All I care is boat ID. I use those boat ID to naturally join with reserve. So I put out boat ID before I do the natural join with reserve. And using the same argument, similar type of argument, after the natural join with reserve, all I care at this point is sailor ID. Who has reserved those red color boats? I don't care about what date and what boat they have reserved. I only care about who reserved those red color boats by their sailor IDs. Then I use those sailor IDs to join with sailors. This query, as you can tell, is much more efficient than the query above. Why? Because the number of tuples or number of values involved in the join is much reduced. A join is very expensive, as we all know. If each table has n records, join in the worst case may reduce to n squared cost, right? Like the cost of doing cross product. So if you can reduce the size of the input to a join, your efficiency for the join is much better. You all follow this argument? Henceforth, the second query is more efficient. However, the point is, for a database system, you as a user of the database, you don't really have to worry about these details. The database system, as I mentioned at the beginning of the course, a great feature of that is you only ask what you want, but not really how to do it. But we also said for relational algebra is operational, meaning that not only you are specifying what you want, like who will the regular vote, you are also telling the underlying system how to do it. Comparing the two solutions, obviously it's very operational, right? You are telling exactly in each step what you're doing. Do you see this argument? What really happens, now after understanding this example, what really happens in a database system is the following, which is I take a relational query as input, SQL as input. SQL, as we will quickly see today, only tells the underlying system what to do, but not how to do it. And that SQL query will be represented using a relational algebra form. Then the underlying database engine will take a relational algebra query as its representation and morph that into another relational algebra query, hopefully more efficient. Meaning that I take the first relational algebra representation as the input, which map to the SQL query the user has given to me. Then using some magical procedure, I arrive at the second plan down below, what I call a query plan, which gives you the same output, but using a different operational approach. That's more efficient. And this magical process is called query optimizer, which is a big part of why a database is very successful today. Because query optimization is a really complex procedure, and nowadays commercial database can do a really good job at that. In fact, I can tell you query optimization is an NP hard problem, which means unless P equals to NP, it is hopeless to get a polynomial algorithm to find the optimal plan. in terms of efficiency. Okay? Okay, so that's so much I want to talk about in this slide. Let's move on to to more examples. What about facilitator who reserve a red or a green boat? Continue from this discussion is tempting for you to say, okay, here I find facilitator who reserve red color boat, right? You want me to find red and green? I will simply change this condition to color equal to red and color equal to green. That gives me the sailors who have reserved a green or a red color boat. Do you follow what I just said? How many say that will solve that curve? How many say this will, by modifying the curve condition to simply say color equal to red and green, will give me answer to this curve? You said no. Can you explain? The answer is no. Yes. Yeah. But can you explain why?
Because you're using and.
You're using and. When you're using and, you actually get nothing out of the boat table. There are no boats that red and green have the same property. So
you use or.
You use or. Yes. Okay, that's it. And in this case, because my query condition becomes so complex, I'm gonna rewrite my query using this renaming operator. If you guys still remember this renaming operator goal, what I do is, first of all, I select those red or green color boats from boats, and I rename that called temp boat. So I introduce another relational instance called temporary boat, which holds all the red and green color boats. You follow that? So English language and logic doesn't really match up one-to-one, right? When I say that instance holds both red and green color boats, but in order to get that, you need to use or instead of and. Right? So human language doesn't really match up with logic operator all the time. Sometimes they match, sometimes they don't. You have to be a little bit careful. Now, with that defined, and then I will take this temp boats, natural join will reserve the sailors and put out the sailor name. Okay, now find the sailor who reserve a red and a green color boat. How do we do this? Since red or green color boat is to use or, it is a hint to say that for red and green color boat, we just change this condition to and. Obviously, no. If you use and, there are no boat in temp boats. There are no boats color both red and green. Impossible, right? Each boat is colored either in red or green. Cannot be red and. You cannot tell me, oh, this is red and green. Right? It's impossible, right? So what do? How do we solve this first? Well, you can use intersection. Right? For example, you find all those sailors who reserve red color boat. The sailor IDs who have reserved a red color boat. That's what this query does. All of you follow this? And similarly, I find all the sailor IDs who reserve a green color boat. Then I join them. Sorry, not join them. I intersect them. This will give me the sailor IDs who have reserved both red and green. Then use the resulting set of sailor IDs and natural join with sailors and put out the sailor name. All of you follow this discussion here? Yeah, no problem? Okay. Find the name of sailor who reserve all boats. Remember, the reserve table shows you which sailor ID reserve which boat ID on which day. And the boats table has a list of boats. What this query asks you is, which sailor ID has reserved all boat IDs from the boats table? And once you find those sailor IDs, you join with sailors to find out their name. That's what this query asks you to do. Now, I pause here and ask you guys a question. What's the operator you have to use in order to solve this query? There's one particular operator that's of really importance to this particular query.
Is it division?
Division, right? This bears a whole lot of similarity to the example we talked about for division, which is which student has worked on all projects, which sailor has reserved all boats, which student has taken all courses, which professor has taught all students. All of this bear the same structure. You see that? Yes or no? meaning that for each boat ID, I need to find a pair in the reserve table showing that the same seed ID has reserved that boat ID. If I write down my logic, what it looks like is I'm trying to find those seed IDs such that for any boat ID from boats, there exists a record. What record? This seed ID, particular seed ID, and boat ID, and some date. I don't care about which date it is. Some date from the reserve table. That's essentially what I'm trying to find. This is all the seed IDs we reserve all the boats. Really important to note that I'm using some date. I'm not using a particular date. I don't care which date you have reserved that boat. As long as there's one reservation record showing you have reserved this boat, I'm okay. You follow this argument? So that's essentially what we want to do. How do we translate this to relational algebra? Well, if you look at this structure, first of all, you say, I only care about the boat ID. I don't care about the name or the color of the boat. So I put out boat ID from boat. And I divide that by what? All the possible combination of seed ID and boat ID from reserve. So I put that out seed ID, boat ID from reserve. That's it. And the resulting schema of this, by the way, what's the resulting schema of this? Sealer what? Sealer is
ID.
Yes. The resulting of this is sealer ID. Remember, I talked about when we do A divided by B, what are the two requirements? Really important requirement. When you do A divided by B, the schema of B must be a subset of schema of A, requirement number one. Requirement number two, the resulting schema is the difference of the two schemas. Meaning this, all the attributes in A minus away the attribute in B, that's the resulting schema. All of you follow this? Henceforth, it's really important to do this. You cannot discorrect. If you take this divided by both, this is wrong. Why? Because the schema of both is what? Seed ID, boat ID, and date. Schema of both is boat ID, name, and color, right? Both name and color. If you were to do this, what you are saying is you are trying to find those records in reserve that match with each record in boat. I can tell you there are no such reservation record because in the reservation table there is not even a name and color attribute, so it's impossible to find any such combinations. Does that make sense? Henceforth, you must make sure the schema of B is a subset of schema of A in order for you to do division in the first place. So this is completely wrong. You cannot do this. So you say put that out boat ID. But now the schema of this is boat ID, which is a subset of SID and boat ID. Now I want to point you to another query, which is what if I just take reserve and divide by boat ID? What do I get? What's the difference of the two? Can someone tell me? What's the difference of these two queries?
You'll get the other fields of reserved as well?
You get, yes, that's the literal difference of the two, which is very good observation. You're saying you got other fields of reserve as well, which is seed ID and date. The date that the boat is reserved. But can you tell me the semantic difference of the two? That's the literal difference of the two. What's the semantic implication of this? What do you get in the end? Do you find sailor who reserve all the boats, or what? You got duplicates on the dates? No, you don't get duplicate. You get duplicate on the dates, yes, but that's by different sailors. That's.
You're getting all the boats that are reserved.
Say again.
You're getting all the boats that are reserved.
You got all the the output schema doesn't even have boat ID in it. Over there?
You get the information about all the sailors who have reservations on a date?
No. If to do that, all you need to do is do a selection of sailor ID and date from reserve. That's it. Right? Why you bother to do a division? So, okay. I think we all need to go back and look at the definition of division, which means, okay, just now, if you come into the midterm in the state you were in 5 minutes ago, you would not be in a good state. But the good news is you still have a lot of time to prepare you to a better state. Okay? We're not to launch that rocket yet. There's still time. If you were to launch the rocket like that, we'll fail. I tell you that. You will call Houston. Okay? No? You call Houston when you have a problem. Okay? You don't call Houston when you don't have a problem. Okay, so what's going on here? Okay, let's look at the definition of division. Definition of division says you are trying to find all such values, in this case a pair of values, that pair up with each of record B. Record B in this case is single boat ID, a list of boat IDs. So what you're saying is I'm trying to find all the sailor ID and date pair such that given for any boat ID from boat, there exists a sailor ID and that particular date with that boat ID from reserve. Look at the difference of the two. Here is some date. I don't really care about what date it is. Here is some specific date. Can you now tell me what's the difference of the two?
So you get everything in R basically. You get all the tuples of SID dates.
Yes, that's the literal meaning of the output, right? What's the semantic meaning? I mean, think about this, right? You're getting a particular sailor ID value and a particular date value, such that that particular pair of values combine with all the boat ID from the boat table, in the reserve table. What does it tell you?
You're looking for somebody who got all of the boats on the same day.
Yes, you find the sailors who reserve all the boats on the same date. That's different from the query to the left, which is sailors who reserve all the boats, period. I may reserve all the boats on different dates. But the second query is more restrictive, saying that you must reserve all the boats on the same date. That's the difference of the two. Do all of you follow this? The reason that this query get rid of the date information is because I project away the date value before I do the division. So I started with my A, quote unquote A, start with only the combination of sailor ID and boat ID. Date is no longer relevant. Here in my division, my A here, A divided by B, this is A, you reserve it to A, has the date information in it. So you end up with the difference of these two. Okay? Alright, so that's enough discussion of this. Okay? And of course, finally, you natural join with sailor to get the name of that sailor. For each boat, find the sailor with the smallest sailor ID who has reserved this boat. This takes relational algebra query to another level, right? In terms of how difficult it is, right? Why this one is difficult? Because if you think about the discussion we had on relational algebra, we never talk about aggregation operator, min, max, count. Like for example, a simple query like find out how many times a sailor has reserved boat 1 or 3. A simple query like that, you will not know how to do that in relational algebra because there are no aggregation operator, there are no count, no sum, no min and max. Does that make sense? So you may wonder, is it even possible to do this query? Because it seems like in order to solve this query, I need something like a minimum operator. Smallest, right? I need to have something like minimum. But in fact, you can still do this query without any of those operators being introduced, without any of those aggregation operators. Okay, how is that possible? Let's look at this together. So here is what I will do. I take a reserved instance, I rename that into R1, SID1 and boat ID1. I put that away the date. I don't care about the date. Because you only asked me who reserved that boat with the smallest CID. You didn't ask me the smallest CID reserved that boat on a particular date. So date is irrelevant to me. So I put away the date. And I take the same construct, I make another copy of that instance. So what I'm doing so far is nothing but producing 2 copies of the same instance. That's what I'm doing so far. All of you follow this? And each copy shows me who reserved what. That's it. Who reserved what? Which sailor reserved which boat. Okay? Now, in order to find for each boat the smallest CID you reserve that boat, what do you do? Well, if you join the 2 copies, if you join R1, R2, and make sure that you're talking about the same boat ID equal to boat ID. However, CID is greater than another CID. What that tells you? What that tells you is for all the reservation made on that boat, on the same boat, I can differentiate who has a larger CID value, who has a smaller CID value. I don't know who is the smallest, but for any such pair, I can find out who has a larger CID value, who has a smaller CID value. Then I keep those ones who has larger CID values. The trick is that sailor ID with the smallest CID value would never appear in that larger side. Everybody else will have appeared in the larger side, except the smallest one. That's how I solve this problem. That's it. Okay, so that's the idea. I do a natural join, not a natural, I do a condition join between the 2, such that boat ID equal to boat ID, CID 1 greater than CID 2. So for all those sailors who reserve the same boat, I check against them, and I keep the one with larger CID value, which is CID 1. This tells me all the sailors who reserve that boat, but the guy with the smaller CID. Then I use the entire instance subtract away from that. I call this IR, larger reserve. The one with larger CID reserve that boat. I take the entire instance, subtract away those. What do I get? For each boat ID, I get the smallest CID who reserves that boat ID. Okay? Okay, now I change this query a little bit. I say, okay, how would you change the query to answer this? What changes you have to make? Go ahead. Yes.
Flip the greater, or flip the.
Flip the greater than, or put that out sailor ID 2. Instead of put that out sailor ID 1, you put out sailor ID 2. Okay? The rest stay the same. Oh, there's another example with the largest rating who reserved this boat. This I will ask you to read yourself, and I will skip this example. I mean, the construction is somewhat similar to what I have just said. For each boat, find a sailor with largest. So the idea is you natural join with reserved sailors and make 2 copies of that. Then you do a self join between the 2, saying that boat ID is the same, sailor ID is different. One has a smaller rating than the other. You keep all those with smaller ratings. Then finally, the one with largest rating will not show up in this. You take the whole instance, subtract with this, you get the sailor ID who reserved that boat with the largest rating. Okay? So that's kind of the idea behind this construction. Summary, you can get this offline, so we're done. So let's move on to the next topic. Okay, next we're going to talk about SQL, structured query language. So from the end of that relational algebra discussion, you can tell that those seemingly simple operators can become really tricky. In fact, it is very tricky. And so this is an early sign to say that you have to spend some effort after lecture to study in order to do well in midterm and homework. Right? If you just come in here every day for the lecture time without reviewing what I said in the lecture, then you will not, I think for a lot of you, you may not be able to catch up. Okay? You do need to spend some time after each lecture to review and to practice. That's the key. Right? No matter how many times I iterate the concept over with you, it's always the best you try to solve a problem yourself for once. Okay? That's much better than me going over the same concept millions of times. So practice is the key. Okay? And don't underestimate how tricky it is to write some SQL queries or relational algebra queries. Okay? So next, we're going to talk about SQL. Now, with the understanding of relational algebra in place, understanding SQL becomes not so hard anymore. Right? Now we know what's selection, what's projection, what's cross product, what's join, what's blah blah, what's division, all that. Now it's ready for us to talk about SQL and how we map those concepts in relational algebra into SQL representations. Okay? So first of all, let's take a closer look at the create table statement. Okay? Because that's kind of the first thing we need to do, right? In order to have a database, you have to create a table in the first place. Okay? So for that, I will show you what create table looks like in a real database. Oh, wrong password. Okay, so I have a bunch of tables on this one. I can show create table, for example, on course. So this is the create table statement of that table. Okay, somebody typed this at some point in time to produce that table. Okay, so what are all these different things means? Right, that's essentially what we're trying to do here. The way to read this is to read this as regex expression. Regex means regular expression. Okay? Regex means regular expression. So what that means is the following. So I'm going to talk about the convention. The convention is whenever you have capital letter words, those are system reserved keywords. Whenever you have small case letters, those are user supplied parameter values. In practice, in real systems, they don't make such distinction. Even for system reserved keyword, you can still use small case letter when you type your create table statement. For our lecture, to make it clear, I differentiate the difference of the two using small case and capital letter case letters. Now, that being said, the convention is I have create table, the system reserved keyword, followed by a user supply parameter value called table name, followed by a bracket. Inside the bracket, I have a list of column name and date type. And potentially with the default value, in regex, regular expression convention, square bracket means that's optional. You may or may not supply a default value. That's essentially what it means. And you may or may not supply what we call a column constraint. At the end of the day, you may or may not supply a table constraint. Okay? So that's the convention of this. And column constraint can be one of the following. Column constraint start with the keyword constraint with a constraint name, but this is optional, meaning that you don't have to give a constraint name. You can go directly to the definition of your constraint. This part is optional. The possible choices, multiple bar in regex means alternative choices. Means you choose one of the following. That's what multiple bar means in regex. Okay? So column constraint can be one of the following, not now. When do we use not now, by the way? We talked about this.
Bold line?
Bold line, right? When you convert relation model to, when you convert ER to relation model, when you have a total participation constraint, you may need to use not now to enforce the fact that you need to specify value for that. I will give you a specific example of that in the next slide. And null value, meaning that the default value is null. If you don't specify value for it, or unique, means that this is a candidate key. You can also specify somebody as a primary key. You can also use a more advanced operation called check, followed by a Boolean expression, such as age must be, student in my university must be at least 18 years old. How do you do that? You say, after the age column, you say check, followed by a Boolean expression, which is age greater than or equal to 18. Okay? You may have references, which is to specify, let me finish and I'll take your question, which is to specify a foreign key for the current column. And for the foreign key, you may also specify on delete what's your action, on update what's your action. Remember the referential integrity constraint discussion we had? When somebody is trying to delete a record who is a foreign key in another table, you should do one of the following. One is no action. You allow the deletion of that record with that primary key value to happen, or you cascade, meaning that if you try to delete the student record, you should delete all the enrolled record with that student ID value. That's what cascading means. Or set now means that you allow the deletion of the student record to happen, but then those records with that student ID value, which is the foreign key in the enrolled table, you set those student ID value to null to avoid this dangling pointer challenges. I'll set to some default value, maybe not null, but let's say 1111. That denotes all the deleted student ID value in the enrolled table. So those are the 4 possible options for you to specify when you have a foreign key. One of the four possible choices for enforcing referential integrity constraint. Now, with that being said, I take your question. Yeah, go ahead.
Does primary key imply unique?
Yes.
Okay.
Yes. Primary key, of course, also imply is unique.
Yes. Does primary key not null? Like, does that imply not?
Okay. Very good question. Does primary key have to be not null by default? Yes. Whenever you specify something is primary key, or in fact something is unique, candidate key, it cannot be a null value. Because null is not unique. Think about it. It's automatically implied. Okay, with that being said, let's look at the last one, which is table constraint. So the difference between table constraint and column constraint is as follows. They are very similar, which is for you to specify some sort of constraint checking. The difference of the two is column constraint involve that corresponding single column. For example, check age greater than or equal to 18. Only involve the age column. Table constraint is a constraint which involve the expression of that constraint involve more than one column of your table. Henceforth, you cannot attach it to any one single column. You have to attach it as a table constraint because it involves more than one column. So that's the difference of the two. You follow this? Example, age must be greater than 18 years old, greater than or equal to, and name must be not. Name must not be some strange values like AAA, whatever. I don't know. I mean, think about a word that you want to prevent somebody to be named after. Okay? And you want to check both conditions at the same time. You want to use a table constraint for that because it involves multiple columns. That being said, you can always take a column constraint and express that as a table constraint. The reverse is not true. You may not always take a table constraint and convert that into a column constraint. Okay? Okay, fantastic. Let's look at some specific examples. Suppose I have a table of fields, okay, which has the following attributes, has a code, which is the primary key, like an identifier number for that field. You have the title, you have the DID, the director ID, who directed that field. You can imagine where that DID comes from. Most likely, I didn't specify this as it's a distributor, not direct distributor. Who distributed this film? So you can imagine is this table is actually a result of this ER diagram. You will have, obviously you have a film table, film entity set, which has code as a key, as title, as an attribute, data production as an attribute. Kind, I think it's like the category, the genre of the film. So, okay, and DID. There is a distributor entity set with DID as a key and a bunch of some other attribute. I don't know, maybe name and whatever. Now there is obviously a relationship set between the two. For example, is distributed by which film is distributed by which distributor. You follow this? The fact that I'm taking DID from the distributor to the film table, what does it imply? Can someone tell me?
That it's many to one with the arrow.
From which to which?
The film has the arrow.
Yes. So it's a one to many like this. One distributor distributed many film, but each film is distributed by a single distributor. Because of this, when you convert this to tables, this schema is DID and whatever other attribute it has. And here, because it's one to many, so the setup is kind of like this. You cannot have, this is impossible, you cannot have another distributor distributing the film. To uniquely identify this line, all I need to do is take the DID value and place together with this entity here in order to uniquely identify the line. So I don't have to create a table for it. So I end up with a schema like that. Okay, that's what we said before. Okay. So I hope you guys can do this, meaning that by now, looking at the schema, you can kind of reverse back to the corresponding ER. Do you follow what I just said on the whiteboard? Okay. Now that being said, DID become a foreign key, but not part of your key. Your primary key for the table is still just code. You don't need to include DID into your key to identify a film attribute, a film record. Okay? In order to identify this dot, you still just need code, but you don't need this DID value. DID is just a foreign key. Yes? You follow this? Now, this schema also says data production is unique. What that tells you is in the specification, somewhere somebody mentioned that on a particular date, there's only one film being made. Of course, this is not a realistic setup, but imagine that's the case. There's only, on a particular date, there's only one film being made. That implies data production is the key as well. All of you follow what I just said? And I add a foreign key referential integrated constraint and says no action, means that even if the distributor is to be deleted, I do nothing about those values I borrowed from that distributor into the film table. Meaning I keep the DID value, even if the corresponding distributor has been deleted. But two questions over there. She goes first.
Is production just a given name for the constraint?
Say oh yes. Production is just a given name to that constraint. Yes.
Is that necessary? You have to give
you don't have to. You don't have. If you don't have to do that. Yes. If you go back to the regex expression, that constraint name, I think we talked about this somewhere. That constraint and constraint name is enclosed by bracket square bracket. That indicates in regex expression that means it's optional. It's optional. And some other question somewhere. Go ahead.
The default on the way to have no action.
Can you speak louder? Oh, it's a default no action. Yes, default is no action. If you don't spend any if you don't specify anything for foreign key referential integrity constraint, the default is that. In fact, I want to extend your question a little bit more. In commercial database engines, the most commercial database engines, including the one we're going to use as our server, by default, the engine actually disable the enforcement of any referential integrity constraint. Meaning that even if you specify, for example, undelete cascade, which is to say if I delete that distributor, I'm going to delete all the fields associated with that distributor, right? If you specify undelete cascade. Even if that's what you have specified, the database engine may do nothing when that distributor is being deleted. The reason for that is enforcing constraints in a real database is expensive, as you can imagine, because enforcing constraint means that the database server, has to monitor every single action down to the involved tables. You follow that? If somebody delete that distributor or somebody update that distributor PID, I need to closely monitor every single such activity, which can be really expensive and introduce a significant burden on that database server. That's why a lot of database engines by default disable that. So if you don't observe your database enforcing your foreign key referential integrity constraint, don't be panicked. That's simply because the database server is configured in such a way that check is disabled, regardless of what your expression is. All of you follow what I'm saying? Fantastic. Yes?
Does that mean that you'd have to go manually delete?
Yeah, I mean, if you think about it, it's really how critical your application is. If you're running Department of Homeland Security database, you want to enable this constraint, right? If you're running University of Utah database, I don't know. Right? Do you guys have one? For Department of Homeland Security, no matter what's the impact to efficiency, scalability, they have money. They buy a big server, right? What they care is security, reliability, right? For University of Utah, the chance of somebody hacking into your database do funny things is low, right? I don't know who's gonna hack into your database. Maybe you guys will, I don't know. Increase your GPA, who knows? One more minute, let me finish this. So the distributor table is down below. Here I introduce another constraint. I say BID must be greater than 100. What that means is, okay, BID, even though it's a decimal value, but I want to start with 101. I start with 1. Instead of start with 001, I start with 101. That's what I'm saying. And name must not be an empty character. By the way, this is the table constraint, right? If the condition is AND for your table constraint, you can actually represent this constraint using two-column constraint. You say check BID greater than 100 and name check name not equal to empty character. The effect of those two column constraints combined is exactly the same as the table constraint. If I change this to all, then you will not be able to use column constraints to represent the table constraint. One question over there, then we adjourn the class today. Go ahead.
Can the check constraint reference other tables?
Not really. I talk about this. You're jumping ahead. That's a very good question. We will talk about that next lecture. Okay? Fantastic. Okay, see you guys on Wednesday.